In this section of the tutorial, I will show you advanced capabilities of Eager Pro applied to the analysis of arsenide addition experiment. Now, let's assume that we have three different conditions for which we want to compare assembly and disassembly dynamics. And the replicates for those conditions are in these shown wells. I can make use of this window where I can select the replicates, Control C, and then make a graph of the desired measurement. In this case, it's going to be punctate density by cells area, but you can perform this analysis for any other measurements. So here it is. Now I prepared the graphs for the other conditions already. I also applied averaging and prepared the averaged curves for these replicates. Now let's see how best we can quantify and present these curves. The first thing I'm going to do, or I did, is to put all these three curves in one graph. Let me go ahead and close the windows or graphs I don't need at the moment, or hide them from the working area. So, and before going any further, I'm going to create a duplicate of this graph and hide one of them. So it's always a good idea to do that, because in case the changes you apply to the graph are not desirable and you cannot reverse them. So what do we see here? We can clearly see significant differences in these curves, representing those three conditions that we are comparing. Next, I will show you that despite the presence of these unsightly dips, which are due to wash steps, these curves are perfectly good to quantify. These dips are merely cosmetic. Now there is a way to correct for those, and we'll get to that. Also, while quantifying these graphs, I will show you more tools that will be useful to you to prepare figures for presentations and publications. Let me illustrate. Let's say I want to annotate this graph and I need more space around the graph within the window. I can simply grab one of the axes and drag it, and that creates a space. But if I want to create space on top or the side, then I need to modify the properties of the axis. Double click on it, and then here I can select to draw this axis between 0 and, let's say, 75% of the window. And this is that offset that we created earlier by dragging the axis. You can actually type in the offset value here. I can do similar changes to the bottom or x-axis, and if I choose to draw it between 0 and 75%, that will open up space from the right side of the graph. If I press Ctrl T, then I will activate this toolbox that will allow me to draw various geometrical shapes and place a text. So I'm going to use this annotation exercise to define the quantitative parameters or numbers that we are going to extract from these curves. We're going to extract four different quantities from these curves. Number one is some sort of number or quantity about the cell's ability to form stress granules, and I'm going to call that punctate density at steady stress state. I'm going to show you a little tip here. If I want to make this SSS subscript, then I place the cursor in front of it. Then I can choose subscript, and at the end of that portion of the text, I need to switch back to normal. So this punctate density at steady state, steady stress state, is the value of the curve taken from this region. Now I'm showing you how to make a line with an arrow. I'm going to put an arrow at the end. I can change its color, thickness. There we go. So this puncture density at steady stress state is value of the curve taken from this time window. For the green, it's here. Now, you can average the value from this window, or you can just choose one specific time point for simplicity's sake and let that be 100-minute time point value in this case. Now, why this time window? Because this time window is not only free of these wash step artifacts, it is also more reliable compared to the max value we could potentially use. Typically, stress granule assembly and disassembly process has different phases. First, rapid puncture formation shortly after the stress, reaching a maximum value in the number of puncture or density, and then a rapid decline in the number. And that first initial decline is due to fusion of the small puncture. It's not due to disassembly. These blue and red curves resemble that behavior, but the process is not accurately captured here due to poor temporal resolution of the instrument that we used. I would argue that the process is fast, even too fast for spinning disk imaging systems, where we image every 30 seconds. But here in the plate reader experiment, where we image every 3-4 minutes, we are definitely missing this max value point, or we're missing the maximum value. We're not capturing that. And that's clearly visible in this green curve. As you can see, this max value is almost the same as the value at this steady stress state. This steady stress state is defined by very slow change in the number and size of the stress granule. So after this initial decline due to fusion, there is a phase where cells are not changing the number or the size significantly, and that's what I'm calling this steady stress state. And this number is much more reliable to use as a reference compared to the maximum value of puncture or puncture density. Now the second parameter I want to define is half assembly time, and that is time needed to reach half of puncture density at steady stress state. And that time corresponds approximately to this value for the red and blue curves. Now the third one I'm going to define is, you probably can guess now, half disassembly time, and that's the time to decay to half value of that puncture density at steady stress state, and that value corresponds approximately to this time point. Let me put an arrow on that one as well. I double clicked on it, so at the end, there we go. Now the fourth one is going to be down here, and I'm going to call that residual or persistent puncture fraction. Now that would be the ratio of let me change this here. Fill mode is no fill. So this fourth quantity would be the ratio of this plateau value to the puncture density at steady stress state. So this would be in percentage. For example, for the red curve, if this number reads about 20, then the ratio of that 20 to 150 or so is going to be that residual puncture fraction. Now that we've defined what to measure, let me show you how to actually extract those numbers. And I'm going to work with the version of the graph that was not annotated. It's easier to see, and I'm going to close these windows or hide them. Now, the easiest way to read the numbers corresponding to the puncture density at steady stress state is zooming into the graph and reading the values off of the curve. Let me create a table so I can record those numbers. So in the first column, actually, I'm going to enter some text information. Condition 1, condition 2, and condition 3. Well, in your case, you can be specific and enter the mutation number or some other information that is relevant to your experiment. In the second column, I'm going to capture the values of puncture density at steady stress state. So you can just with the mouse draw this marquee box around the curve, and you can expand the region, thus zooming into that portion of the graph. And if you hold the Alt button here, you can pan left to right or up and down. So I'm going to pan to left so that I can precisely read the value at this time point. So let's call that 103. And I'm going to pan upward to read this the values for the other two curves. This one, let's call it 148, and for the red one it's 154. Of course, you can zoom in and be very precise, but for our demo purposes, this is good enough. So if you right click on the curve and select auto scale axis, you can get back to this view. So now we have the first parameter measured. The second one is going to be half recovery time. You can do the same thing by zooming into the region, but there is a better way to do that. There is a command called find level, and if you want to look up how that command is used, you can right click on it and look up the help. So find level with the name of the command and then a few parameters, name of the wave that you want to measure the level, and then that level value. So we're going to use this option or parameter here because it specifies the X range of the wave to search. Because we can search this portion of the graphs or the process to extract the half assembly time, and later on we have to do the same thing for the disassembly side of the business. So find level R equal, I'm gonna search from 0 to, let's say, 50-minute time point. Then I need to enter the name of the wave that I want to search, and the easy way to look up the name of the wave is by going to the graph. If you right click on that curve, you can copy the trace name, and then you can place it here, comma, and the value is half of this characteristic value or the puncture density at steady stress state. So for the condition 1, that would be 51.5. So the x value corresponding to that y value is 28.28, 28.3. 28.3 minutes. I can repeat the same command for the other two curves. I'm going to look up the name for the blue one. The half value for the blue is half of 148, that is 74. And the time is 16.5 minutes. Now let's repeat it for the third one, and the half value for that is 77. And the time is 18 minutes. There you go. So that would be half assembly time. Now half disassembly time, I'm going to repeat the same command. The only difference is I'm going to define a different time window that captures the range that I'm interested in searching. So that would be, let's say, from 100 and upward. I can define 100. It can be infinite, because if there is a alright, so this one is 158.57.8, 157.8 minute. That's the time point where the green curve reaches half of this puncture density at steady stress state value. Similarly, I can perform the same thing for the other two. So this one is 158.3, and the last one is 199.200. So now we extracted these quantitative information that was visually observed. And what was visually observed, that the assembly time for the red and green are very similar, and we can see that that's 16.5 and 18 minutes. But it's way different for the green one, 28 minutes. On the disassembly side, the disassembly times or half disassembly times are similar for the green and blue, and we can see that here, and it's way different for the red curve. So, and the only thing that's left is to read, let's say, the plateau value, and that is again easily done by zooming in and reading the value. So let's say that's 15. For the green and blue, those numbers are very small, so let me call them 0 for simplicity's sake, but you can look up and put actual numbers. But for the red one, the number, the plateau value was 15, and the puncture density at this point is 154. So the ratio is about 10%. So that's 10%. So now we can make nice bar graphs using these values, so that there is no need to use Excel for making the bar graphs, and I will show you that next. Making bar graphs are very easy. From Windows, New, you go to and select Category Plot, and from this list of the waves, you need to find the waves that you want to plot, and in this case I'm going to choose wave 1 and 2, though they are half assembly and half disassembly times, and I'm going to plot them against the names of the conditions. Here's the bar graph. I'm going to change the color of one of them to blue, change the range of display from 0. So there you go. Now I'm going to change the tick marks to the center. So if this is not selected, this is how the tick marks are placed in bar graphs. And also in this window, I can change the gap between categories like this. Also gap between the bars. So let's say this is the final graph that I prepared, and I want to use it in a PowerPoint presentation. We can just copy this by pressing Ctrl C, open PowerPoint, and paste it, Ctrl V, there you go. You can also save this as JPEG or some other image format by going to Save Graphics, select the type, select the resolution, do it, and then let's say give it a name. Now it is saved on the hard drive as a JPEG file. And one other thing is very useful and powerful I want to show you is layouts. Let's say I want to put these three objects, the table and these two graphs, in one layout. The easiest way to do that would be from window browser. So here I'm going to select these graphs that I am interested in, the table as well, and on the selection right click and select new layout. You can modify the sizes. So now I have these three objects in one layout. So this is a useful way to organize the data. You can add new pages to the layout either by pressing the plus sign here or right click and append page. You can directly drag and drop graphs from the window browser tool. As you might have noticed, this layout becomes part of the window browser as well. Now I'm going to show you fitting procedure to correct for the dips due to wash steps. I'm going to hide the windows. I don't need it at the moment. And we're going to do fitting on these three curves. The fit procedure I'm going to use is under Analysis, Multipeak Fit, and Start New Session. You need to select from Target option to select the curves from the current graph. If you hit Continue, it will open and prepares the fitting procedure for one of the curves. There are two ways to get started with the multi-peak fitting procedure. As reflected in this quick tip, you can let the software choose the peaks for you by pressing this button, or you can draw a marquee box, right-click, and assign peaks manually using this window. But before that, we need to create a mask wave and use it under Options over here, so that the points corresponding to the dips are excluded from fitting. The way to create a mask wave is to create a duplicate copy of the original wave. I'm going to right click on the curve and copy the name of the trace or the wave, and from the command window I'm performing the command duplicate, the original name, and the name for the mask wave. The next, I need to edit this new wave. This allows me to access and manually edit the points. Now all I have to do is assign 0 value to the points that I am trying to exclude. In order to figure out which points I need to exclude, I'm going to press Ctrl I, and place a cursor on the curve. And starting from point 12 through 17, I'm gonna assign values of 0. So 12 through 17, 0. Now the second dip starts, let's say, at point 24, and it needs to be until 31st. So 24, there we go. This is a very simple way to create a mask wave. Now we have to select this wave from the list of the waves, and when we do the fitting, these points which correspond to 0 values will be excluded from the fit. Now I'm going to let the software choose the peaks for me. I'm going to press Auto Locate Peaks Now button. As you can see, software found 4 peaks using these estimated values from the original curve. Now I'd like to emphasize that while being powerful, this multi-peak fitting procedure is quite temperamental. What I mean by that is that the final result will depend not only the number of peaks, the type of the peaks, it will also depend the initial placement of those peaks, their height, their width as well. So finding good values for all of that is not trivial and requires some fine-tuning and experimenting around. Now let's try to fit the curve with these 4 peaks. This is the result, and as you can see, if I hit the Do Fit button one more time, the shape changed because it's automatically adjusting the parameters of the peaks. If I change the type to different shape or equation, I get different result, but still not good. The only way I was able to find a fitting result that would resemble the typical profile of assembly and disassembly process was using 2 peaks and assigning particular shapes to them. Let me simply delete 2 peaks from this list. Now the peak on the right should be exponentially modified Gaussian, and peak on the left is convolution of 2 exponentials. It didn't quite work well, probably because the initial estimates were off. So I'm going to go back. Now I will try to remove peaks 3 and 1 so that the initial placement of the peaks are wider apart. Change the type, perform the fit. Now you can see that the fit resembles, or fit result resembles, the typical profile of assembly disassembly process. If you keep pressing the Do Fit button, as you can see, the values are changing. It iteratively fits the curve, and at some point when there is not much progress, it will let you know that I'm not making any progress. We can stop here. What you just saw was an application of fitting to correct for these dips in the experimental curve. And for that we used this multi-peak fit procedure. In order to obtain a certain shape which would resemble a real stress granule assembly and disassembly process, we had to restrict the number of peaks to 2, which resulted in a little bit of sacrifice in the accuracy of fitting. As you can see in this portion of the graph, the fit curve does not quite closely follow the experimental curve. Despite being suboptimal, this fit result is good enough to serve as an aid for eyes to qualitatively relay information about the experiment. Let me show you the graph where I performed this type of fitting for all three conditions. Here they are. As I said, these curves are easy to follow and understand what's going on in the experiment. After extracting the quantitative values from these curves, it is even better to represent the data in a normalized way. So it would be a good practice to put the numbers in a table. We actually do have those numbers. Well, you need to reformat this a little bit. So for presentation, present these quantitative numbers in a table and then the graph in a normalized way so that it's very easy to follow. And I normalized it to that 100-minute time point, which I called puncta density value at steady stress state. So I think I will conclude this tutorial here. I hope you find this tool I put together and the rest of the built-in capabilities of Eager Pro useful in your data analysis.